You are listening to The Vocal Technologist. Spoken tech for your ears.
All right, welcome back. We are diving into, well, a whirlwind of technical developments today.
It's a lot.
It really is. The scope is just massive. You know, it spans everything from these really low-level compiler performance secrets all the way up to how companies are starting to orchestrate autonomous AI coding agents.
On an industrial scale, no less.
Exactly. So it's going to be a rapid-fire session. Buckle up.
It is. And our mission here really is to cut through all of that and distill it down to the core insights. We're looking at two big shifts, I think.
Yeah.
First, the philosophical changes in how engineers are even approaching problems. And second, the really sophisticated new tooling that's defining this next era. You should walk away with a pretty thorough, actionable understanding of what's going on.
Let's do it. Let's unpack this, starting with a trend that I have to say feels completely counterintuitive. Why are older, performance-focused languages suddenly surging? I mean, I'm looking at you, C++, it's notoriously complex.
Oh, right.
And yet, C++ and Rust are showing some of the highest growth rates among major languages. Why are we sacrificing developer velocity for raw performance right now?
It boils down to a fundamental reality, and it's a bit of a harsh one.
Okay.
Software demands consistently, and I mean consistently, outstrip hardware capabilities. We're essentially writing software that eats up performance faster than chip manufacturers can even deliver it.
I remember when we all used to believe Moore's Law would just save us indefinitely.
That era is fading. It really is. And the pressure is compounded by these critical computing constraints, power, the physical limits of chip density, supply chains.
Right.
When those factors get more intense, efficiency it moves from a nice to have to a necessity. Developers aren't just asking, does it work anymore?
They're asking, what's the cost?
Exactly. What is the computational and, critically, the energy cost of running this? The focus is obsessively on performance per watt.
But aren't we, I don't know, undoing years of progress? Pushing developers back toward manual memory management in C++ feels like taking on a whole lot of technical debt.
It's a calculated risk, and it's driven by economic necessity. The control you get from those low-level languages lets you manage memory layout precisely, avoiding all that invisible overhead from runtimes.
Like garbage collection and things like that.
Garbage collection, heavy abstraction layers, even language-specific issues like Python's global interpreter lock. When you need to squeeze every last millisecond or joule out of a component, that control is it's irreplaceable.
So speaking of Python, let's pivot to the elephant in the room. It's dominant in data science and AI, but it's famous for being slow. If performance is now paramount, how does Python even survive?
It survives because its ecosystem and its ease of use are just unbeatable. But you're right, the performance challenges are very real.
So what's the fix?
Well, it's why having an unprecedented benchmark of its real-world speed is so crucial right now. Researchers recently did a super deep dive analyzing the actual latency and memory consumption across the whole spectrum of Python usage.
The whole spectrum, like what?
Everything from fundamental constructs and collections to I/O, popular web frameworks, and even asynchronous processes.
That sounds incredibly useful for just pinpointing where the bottlenecks are hiding. So once a developer finds a hotspot, what's the move? How do you inject high-speed code without rewriting your whole app in Rust?
The key solution is WebAssembly, WASM.
Okay.
It is rapidly becoming the go-to for high-performance Python extensions. WASM acts as this portable, secure compilation target, so you can write super specialized fast code in Rust or C++A, then distribute it as a WASM component.
And the end user doesn't have to manage a bunch of complex native tool chains or compile anything.
Exactly. No custom binaries. It just works.
That really does sound like the best of both worlds. Python's usability, speed of compiled code. But I'm guessing that integrating these two worlds is probably a nightmare.
Oh, it is far from trivial. It requires very precise, low-level engineering. I mean, you have to handle memory management carefully across the boundary between Python and the WASM instance.
I don't know.
You also have to correctly deal with WASM's unsigned pointers, which is a bit of a departure from conventional memory addressing, and then navigate specific API quirks in the runtime.
What kind of quirks? Give me a real-world example.
So one issue that comes up a lot involves runtime limitations. in how specific engines like WASM handle store instantiation.
The setup process.
Right, the setup. If you aren't careful, you can hit resource contention or these really hard to debug integration failures. But despite that, it's being deployed successfully to optimize critical Python hotspots, even for embedding things like low-level cryptography libraries.
So it's a vital way to keep Python productive while still addressing that efficiency imperative. That connects really nicely to our next big idea. We've been talking about how fast code runs. Now let's talk about what kind of code we should even be building. There's this theory going around that the next thing will not be big.
This is a provocative thought. It suggests the era of constant, massive, industry-reshaping change. The internet, the smartphone, the cloud, that it might be slowing down.
This anomalous period of exponential disruption is just ending.
Some argue it is, yeah. Because we're rapidly approaching physical and economic limits, so the future won't be another massive generalized platform, but highly incremental personalized improvements.
So if that's true, what's the practical implication for a developer writing code today?
The implication is a massive shift toward bespoke software. If you can't make the general platform way faster, you have to make the software on it substantially smarter and leaner.
And off-the-shelf solutions are the opposite of that. They're bloated.
They're bloated by design. They rely on broad abstractions for features that 90% of users will never even touch. That creates complexity and leakiness.
So they have all this unnecessary overhead built in.
Precisely. But now, since large language models have made creating custom software dramatically easier and cheaper, the whole equation changes. The future is custom-tailored internal tooling personalized for a company's specific workflow.
Okay, this is where it gets really interesting for me. Because if we're generating tons of bespoke code with LLMs, we need systems to manage that AI workforce.
We need an AI orchestrator.
Exactly. Tell us about Gastown.
Gastown is a fantastic example of where this is all heading. It's designed specifically to manage and coordinate an industrial-scale AI workforce. We're talking 20 or 30 specialized coding agents working in parallel on one task.
Wow. Okay, that sounds incredibly complex. How do you manage that many autonomous agents without it just turning into chaos?
They developed what they call the molecular expression of work, or MEOW stack.
MEOW stack, I love it.
It's great, right? The critical components are beads. A bead is a Git-backed, persistent, and composable workflow step. Think of it like a microservice, but for an agent's task.
Wait, what is a bead in practical terms? Is it just a prompt?
No, it's much more than that. It's a codified, versioned action sequence. You can then combine these individual beads into a molecule.
And the molecule is the whole workflow.
Exactly, like analyze database schema, generate a migration script, and write unit tests. The agents then execute these molecules using their internal mechanism, which they call the Gastown Universal Propulsion Principle, or GUPP.
So if Kubernetes manages containerized microservices, Gastown manages orchestrated AI workflows.
That's the perfect analogy. It's built to handle the inherent unpredictability of autonomous agents. It even has a system of worker roles and patrols agents dedicated to just monitoring and error-correcting the primary coders.
That's amazing.
It's the industrialization of bespoke code generation.
So for developers listening who are maybe building their own internal agents right now, what were the biggest technical hurdles the Gastown builders ran into?
The big three were ensuring robust skill support, making sure agents are reliably proficient at niche tasks, then mastering context management for these long, multi-step coding projects.
Right, keeping track of everything.
And finally, solving the puzzle of reliable triggers. How do you kick off these large, expensive, complex workflows reliably based on external events? That trigger problem is particularly tough.
That brings us squarely to the human element. Because even with the perfectly architected system managed by Gastown, a bad strategy will still sink you. Prioritization is a constant struggle.
It is, and here's the key insight. Perfection is the enemy. Teams shouldn't be trying to make perfect prioritization decisions. It's impossible. Instead, the focus should be on identifying and filtering out the common pitfalls.
The anti-patterns.
Exactly. Just make marginally better, faster choices to maintain momentum.
I can relate to this so much. I feel like I'm constantly stuck on tasks that feel urgent, but a week later I realize they move the needle by 0%.
That's one of the most insidious prioritization traps. The list details 10, but let's highlight a few. First, what you just said. Getting stuck on urgent tasks that have very low strategic value.
Firefighting.
All day long. It feels productive, but it obscures the bigger picture. The second is the trap of over-refining work, the perfectionism spiral.
Spending 80% of the time on the last 5% of polish?
Yes, on a feature that was already good enough. And the third major one is neglecting long-term systemic issues in favor of quick fixes, which just guarantees the firefighting never ever ends.
We're moving so fast with AI generating code, it sounds like we actually need to slow down the human decision-making part to avoid those traps. Which brings us to a really counterintuitive idea: slowing down AI on purpose.
This is a radical but demonstrably effective workflow. It's all about maximizing human critical thinking time. Instead of using the LLM to instantly generate flawed code, you use it as a design partner.
Okay, what does that look like?
You focus on rigorous, in-depth analysis to develop a shared understanding of the problem space. And you formalize all of that in a detailed living document before a single line of production code gets generated.
So you're making the AI prove the architecture and the intent before it proves the execution.
Precisely. You're preventing the massive rework cost that comes from having instantly generated but fundamentally flawed code. By slowing down the input, you get much better software quality and, weirdly, a faster overall time to market.
That is fantastic advice.
Yeah.
Okay, as we transition, let's wrap up by looking at some platform shifts, developer freedom, and the environments they work in. There's a major development out of Japan regarding iOS.
This is huge, especially for the global web dev community. Apple's iOS 26.2 and later will now allow alternative browser engines for users in Japan.
And that's for dedicated browser apps and in-app browsing too.
Both. Any experience that embeds a non-WebKit engine.
That is a seismic shift for the Apple ecosystem. But knowing Apple, I assume the requirements for developers are absolutely ironclad.
They are. I mean, browser engines deal with highly untrusted content and sensitive data, so the risk is enormous. Developers have to get specific entitlements and meet extremely strict criteria.
Like what?
We're talking demonstrating functional baselines, proving strong memory safety, guaranteeing timely vulnerability patching, and adhering to strict privacy standards, like blocking cross-site cookies by default. It's a very high bar.
Now let's jump to the other side of the cloud, to serverless. You mentioned a new tool, OpenWorkers.
Right. OpenWorkers is all about giving developers more control. It's an open source runtime that lets you self-host Cloudflare Workers compatible JavaScripts, and the critical part is that it runs using V8 isolates.
For those less familiar, why is using V8 isolates a big deal for self-hosting?
V8 isolates are the same high-performance, lightweight execution environments that power Chrome and Node.js. They're not like traditional VMs or heavy containers. They have blazing fast startup times, low memory footprints, but still provide a robust security boundary.
So you can run thousands of tiny, separate processes securely and efficiently on your own hardware.
And you get the performance advantages without the vendor lock-in. That's the whole point. It has robust bindings for things like KV storage, PostgreSQL S3, all inside that sandboxed environment. It's about empowering developers to really own their architecture.
And speaking of owning your architecture and developer freedom, there's this sentiment that Linux is really having a moment.
Yeah.
That it's finally user-friendly, especially with Windows getting more intrusive. This feels relevant for a show like Vocal Technologist, focused on web dev.
It's true. The argument is simple. Linux is good now. The distributions have solved a lot of the old usability hurdles. And for people who prioritize genuine ownership of their PC control over your data, your environment, it's a very attractive alternative.
You're not fighting against integrated cloud services you can't disable.
Exactly. It's the ultimate tool for a developer who just wants a clean, unvarnished experience.
We have covered a remarkable amount of territory, haven't we?
We really have.
We started with the foundational constraints of efficiency and physics, moved through complex tooling like Gastown needed for this bespoke AI-driven future, and ended with the human elements of strategy and platform control.
It perfectly illustrates the current trajectory, I think. The complexity hasn't disappeared, it's just shifted. We established that LLMs are making bespoke software creation almost trivial, right?
Right.
But then we detailed tools like Gastown with its MEOW stack and GUPP, which are necessary just to manage the complexity of the agents writing that code. We are spending massive engineering effort orchestrating these incredibly complex autonomous AI workflows.
So we're solving the complexity of generalized software, but we're replacing it with the complexity of managing the coders themselves.
That's the provocative thought I want to leave you with. As we build these incredible systems to manage an army of AI coders, are we simply trading one kind of complexity for another, treating the complexity of the code we run for the complexity of the orchestrators we now have to maintain? Think about that complexity curve the next time you design a system.
Spoken Tech for your ears.